Hi all, Dr. Clark here, and for forest management, this time we're going to talk about measuring standing trees. We're going to talk about how to measure height and how to estimate age, and a little bit on canopy cover. And then the next lecture, because I had to break it up, we're going to talk about a little more on canopy cover, and we're going to talk about diameter at breast height, okay, or DBH. Almost all of these techniques I'm going to demonstrate for you in later videos, so you can watch those videos a little bit later, but you'll see me in the field and I'll demonstrate how to do a lot of these techniques. Okay? So I want to start with kind of this comic, mainly because it brings to mind an important story for me about forest research. Okay, so this comic says the philosopher's pine, or the eternal optimist. After 4,000 years, all I get is another lousy ring, like what's left in a bathtub. Maybe next year, something different. Okay, and what that is discussing, for those of you who don't know, is every year a tree puts on two rings, a light ring and a dark ring, okay, which is sometimes called the spring ring and the summer ring, or the spring ring and the fall ring. There's lots of names for it. The softwood, the hardwood. There's all kinds of names for it, but the composition of the wood differs. And so you get this different color of ring, typically one lighter and then one darker, and the composition of the wood material differs. Okay? But that allows for researchers to estimate the age of a tree. Now, why does this bring up research memories for me? It's about a story about a guy named Donald Curry. Donald Curry, in 1964, cut down the oldest tree ever recorded. Okay? And it was a bristlecone pine. In fact, they're called the Great Bristlecone Pines. They occupy the Great Basin region, desert, Nevada, places like that, where high up in the mountains. They don't grow very tall, maybe 20 feet maximum, but they are extremely old. Well, Curry was a botanist by training, and he was actually doing a common method called coring, and he was coring one of these bristlecone pines to see what the age of the tree was. Okay, and I'll show you how to core, and I'll show you the equipment and things like that in a later video. But he was coring a tree, which means basically you just drill into a tree and remove a core, or you remove a sample of the tree. Right. That's what he was trying to do, at least. So he gets into the tree and he can't remove the core. Like, he can't get it to become unstuck. And so what he ultimately does is he cuts the tree down to get his core, his sampler, back out of the tree. After he cuts the tree down, he now has a cross section of this tree, and he can start counting the rings, and he does, and the tree is nearly 5,000 years old. Now, so he goes down in history as, one of the big scientific blunders, because he cut down the oldest recorded tree ever. But that being said, I'm sure that there are other trees that were cut down by logging, corporations and things like that were probably older than this. But he made a big deal of it because he recorded the age and everything like that. Very seldom would ever a logging corporation record the age of a tree. They don't really care. All that being said, there's probably older trees out there. Bristle pine cones trees can get to extreme ages. Not all of them have been cored. Not all of them have been studied. In fact, coring a bristle cone is kind of difficult to get the core back out. They can get stuck fairly readily because you can see as the body of this tree, it kind of twists, and it can make it very difficult to get a straight line, and that kind of woody material just grabs onto the coring bit and it makes it fairly difficult. But at any rate, kind of just brings that kind of thought process to me when we talk about aging and stuff like that. We're talking about some trees that are, 5,000 years old. And you can think about what that means for society, for humans, etc. I mean, there's trees that have been on the landscape, since before modern human times, before the writing of documents and advanced speech, clearly way before the United States was ever discovered. Lots of things, prior to a lot of things. But at any rate, 5,000 years old is old. Okay, we're not going to core any bristle cones, but I will core some trees, and you'll get the opportunity to age those core samples later on. All right, so moving forward, let's talk about how you get the height of trees. Okay, and most of you probably know some ways to do this. One way is to use what we call a height pole. A height pole is basically just a giant rod, a giant stick that goes up, okay, and it has, marks on it at different measuring points from the ground. It's just basically like a giant ruler that you stick next to a tree. These are used often in situations where maybe you're in an orchard, or maybe you're on a tree farm, or something along that line, and you want to know the height of the trees. The trees are, a dwarf variety, or they just don't get very big. So, I'd say height poles are probably good to about 40 feet. And if you're talking about Wyoming, okay, they're good for about 20 feet because the wind will make it very difficult to hold the thing still at 40 feet. All right. The old climb and drop. This used to be the method that we used pretty much all the time. People would put on spurs and rope, and they would shimmy up a tree with a tape measure. They get to the crown of the tree, they drop the tape measure down and measure the tree. That's pretty simple method. It was done for a very long time. A lot of times, if a logger was interested in knowing the height of the tree, so then he can know maybe at what point he was going to top the tree. So maybe he wanted to know, okay, I'm going to cut 20 feet out of the top of this tree. He'd get a full measurement of the 20 feet, whatever, and they'd have to climb the tree to do it. All right, so the tree is measured directly via tape. Now, the last method is by far the most common method, and that is to use geometry. Okay, to use a series of angles, Pythagorean theorem, to figure out the height of a tree. Okay, a squared plus b squared equals c squared. We will go through this method. I will show you how to do this method using both a hypsometer, okay, a digital hypsometer, and a clinometer. Okay, now the two are very similar to each other, okay, but I will use both methods, and we'll see, if the two methods are similar. Now, some of you who might have rangefinders, GPS units, things like that, that's really what a hypsometer is. They take into account prior knowledge of the landscape, and then they can adjust for the elevation. A clinometer is based on the angle from that you are standing on the landscape to the angle that you're looking up at the top of the tree. And a good estimate means that you have to have semi-level ground, because if it's really hilly and you're standing on top of a hill and the tree's in the valley, then that is not a straight line, and makes it much more difficult to get an idea of the height of the tree. You have to actually do two calculations. You have to do a calculation at your eyesight, and then a calculation down from your eyesight down to the base of the tree. And I'll show you how to do some of these to adjust for the different elevations that you might be on a given region. Okay, but again, like I said before, this is really just taking advantage of making a right triangle, knowing that there's a 90 that comes off the tree, and then figuring out the angle and distance, and that'll give you the height. Okay, and I'll show you again, and you'll have lots of practice with that. Okay, so here are some examples of the different tools to get height. Again, this is a height bar, height pole, height stick. In this case, it's just colored, but there's readings on these little levels, so you know what the height is. Some of the ones that are used often by like surveyors, it might be surveying a forest and things like that, they'll have really big numbers on them. So someone that's far away could read those numbers, and as that individual's walking, can get an idea of how the canopy changes. This is some typical climbing gear. You have some spurs over here, tree spurs. I'll show you tree spurs, maybe in action. I might climb a couple trees and videotape it, but nonetheless, tree spurs are pretty simple piece of equipment that's often used by individuals that are going to climb a tree. A harness, a rope system, pulley system. Whoops, I'm sorry. And that gear, that's really for climbing trees. The hypsometer or clinometer. Okay, this is the hypsometer. This is a digital version. Okay, it does it all for you. You just click one point at the base of the tree, one point at the canopy of the tree, and then it'll calculate the height. Okay. In this case, what this picture is showing you is actually what a lot of logging companies are interested in doing, and they're trying to find out, well, how much of the tree is usable. So they don't really care how tall the tree is. They're just going to cut the top of this tree off. This is, the crown of the tree is, maybe it's good for pulpwood or paper milling and that kind of stuff. But for lumber, for merchantable material, you're only interested in kind of this region of the tree. You're not interested in the stump. So a stump height. So maybe you have a 2-foot stump height, and then so you're looking at that stump height. You might make a mark on the tree. You're looking at the region where it's merchantable, the height line, and then you can get that length. Okay. In other cases, in the case that we're going to use it for, we want to know the entire height of the tree for scientific purposes. So we're going to measure it from the base of the ground all the way to the top using a hypsometer and a clinometer. Okay. So again, just some tools of the trade. You'll see them in action, and I'll give you some examples of just data from them, so you can calculate the height using the data that's provided by them. All right, so that kind of picture of merchantable height versus total height, this can be important. So total tree height is important when you're talking about research. Forest managers, when you're talking about fire prevention, wildlife, ecosystem management, these kind of things are important to know the total tree height, because that'll give you an idea of, well, what is the canopy cover going to be like? How much distance should you have between trees if you're trying to prevent crown fires. If you're looking at habitat for songbirds and things like that, well, how much of the tree is considered crown or considered canopy? And and then you can estimate kind of, well, how many nesting sites would that be? How much competition are you going to have with a given tree, etc. Okay, so the total height is often important from that standpoint. It's greatest in conifer trees, mainly because conifers grow pretty much straight. So the tip of the tree is still important. The crown of the tree is still important. And that's true for merchantable tree height also. So when you look at merchantable tree height on conifer trees, they have a much greater length to them that you can actually use as, board foot, etc. Now, as far as deciduous trees, a merchantable tree height is probably a more important calculation because of the canopy, because of the crown of the tree. Normally, the crown of the tree, there's a lot of branching, a lot of splitting, and the wood is not as suitable as, say, a coniferous tree or a conifer tree. So we often have calculations that would go into play or come into play with merchantable tree height. So if you're dealing with, say, a deciduous tree, then you would look at the minimum top diameter. So you're basically going up the tree from trunk to the crown, and when you get to a point where it's 60% of the DBH, if it's a small tree, that's usable. 50% of the DBH for a medium tree, 40% of the DBH for a large tree. These are just rules of thumb when you're dealing with deciduous trees and you're trying to figure out the merchantable height of the tree. So here you might see, okay, the total height, that's just, maybe this is a coniferous tree. Total height is basically this, close to the same as the saw log height or the merchantable height. Maybe a little bit off the top that you can't use, but the total height will give you a pretty good estimate when you're talking about conifer trees. When you're talking about, again, deciduous trees, maybe the merchantable height is right there at that fork, okay? Unless you're dealing with like pulpwood or something like that, and then maybe it's further up in the canopy. Again, it depends on what the purpose of the tree is. If the purpose of the tree is to turn it into, little cooking pellets or wood pellets for a wood stove, then obviously up here in the canopy is still utilized. If the purpose of the wood is to make furniture out of it, or, for board foot or something like that, then, saw logs are much lower out of the canopy for things like that. Okay, so again, depends on the use of the tree. All right, just a brief little bit about canopy cover. So the tree canopy cover can be important for a few reasons. Mainly these are ecosystem management reasons. Okay, canopy cover dictates a lot of what the plant growth on the canopy or on the forest floor is going to be like. It dictates, what you would expect for the trees that are growing underneath that canopy. How much direct or indirect light are they getting? These kind of things are important to predict how fast that forest is going to grow. So the tree canopy cover is the area of the ground that's covered by plant foliage. Okay? And there are different ways to estimate this. You can estimate this kind of I guess one would say the old school method, which is a spherical densiometer. You can see one here. It's basically a circle with a bunch of little mirrors. Okay, and these mirrors are estimated, well, how much plant material is in each mirror. And then you can figure out the percent coverage in different regions. You can also figure out the percent coverage that's covered by conifers versus deciduous trees, and that makes a difference. Remember, a deciduous tree, majority of them, are going to drop their leaves in the fall going into winter. So they only are leafed out maybe half the year. So the canopy cover in a region where it's dominated by, say, deciduous trees, it's less than if it was dominated by conifer trees. And, let's say a deciduous tree canopy cover is 60% and a conifer canopy cover is 60%, then clearly the canopy cover from the deciduous tree is less for a given year because of the lack of foliage in the fall and whatnot. So that's a spherical densitometer. Okay. Now the other couple methods is to use a camera. So you can just put a camera on a tripod and take a picture of the canopy. Using a wide-angle lens, you can take a picture of a canopy and then estimate that. There's ways to do that. You can drop it into Photoshop programs and remove all the color and just examine the difference between the surface of or between the sky and the actual foliage. It's pretty easy to do. I think I'll probably show you how to manipulate photos to do that. And in fact, there are programs that you can stick it in to, and it'll count or estimate the percent coverage of the picture by a given color or scheme or whatnot in the camera method. And then the last one is what we call a GRS sensitiometer, and this is a picture of one. I'll use this often, and this is probably used a lot more often than the other two methods. It's more scientific if you're trying to estimate the canopy cover. The other way to get at canopy cover is to measure how much light is coming through the canopy. That's probably the method that's used by most researchers, but that equipment is very expensive. So something like a densitometer or camera or even a GRS is going to be far cheaper and quicker to set up often, quicker to get numbers, and so you might see somebody packing these pieces of equipment to get at the canopy cover. But it works the same way as the mirror system, except for you kind of looking through this pipe, which has a mirror that shines up to the canopy, and then there's a grid system, and you estimate it via the grid system. Okay. Most of the time, this is done on a line transect. So it's done in a linear line where you might have 50 random points at which you're going to stop and take a canopy cover measurement. And so you're making an estimate of canopy cover across a certain region, a certain area. That's probably the most typical use of canopy cover measurements. The other possible use is maybe you're interested in a single tree and its canopy cover. So at that point, you might take 4 measurements around the tree, one on the north axis, one on the east, south, and west axis, and then kind of average the canopy cover of the entire tree to get at that tree's canopy cover. Okay. All right, tree age. Most of you are probably fairly familiar with aging trees. You probably did it in elementary school or middle school. But we're going to talk about methods to go further than just looking at a general age. Okay, a general age is fine. Saying this tree is 4,000 years old is completely fine. But more importantly, especially from a management perspective, is, well, what was the growth rate? And so maybe the last 10 years have been the hottest 10 years on record in majority of North American forests. So you could pull a core sample and look at the last 10 years and look at the growth rate and say, hey, what's the growth rate? How are these trees doing with these extreme heat indexes? Okay, and then you could look at the 10 years before that, where you might have an average temperature, etc. You might have average precipitation numbers. Okay, there's all kinds of things, but tree age alone is, I don't want to say it's useless, but it doesn't tell you that much information. Okay, so a couple other things that can get incorporated into tree age is by knowing the age of the different trees, you can know a little bit of information about what the age of the stand is. Again, important, okay, from the standpoint of, well, do you have an even age stand? Is almost, all the trees within 20% of each other from an age standpoint? If so, then, you could be subject to maybe a disease outbreak that could affect all the trees in that region. Okay? Do you have an uneven aged group or uneven age stand where you might have 3 or 4 or more distinct age classes, which means that you might have let's say you have a pine bark beetle outbreak and it's affecting all the old trees, but maybe 2 age classes of the younger trees are going to make it. And so you're not going to lose the entire forest to one disease outbreak. And you can predict, well, how much you're going to lose because you know the age of that stand in question. Okay, apart from that, you can also look at the crown class. Okay, so this is often done in conjunction with the age of the tree. So you'll find out the age, and then you'll classify the crown of the tree. Now, in some cases, you're classifying the crown of the tree based on the canopy cover or based on the distance to the nearest tree, these kind of things. But crown class can mainly be broken up into 4 pieces. So you can have what we call a dominant crown class, which means the tree is above the general canopy level. So that tree is getting full sunlight from above. Okay, so this is the dominant tree. It's larger than the average tree in a stand. Okay, codominant. Okay, so it's below that dominant, but it's still getting light from above. Okay, so it's still receiving full light from above. Maybe it's not receiving any from the side, okay, but it's still receiving light from above. Okay, and that's probably the average tree in a given stand, especially in a mixed age stand. That's the average tree. You're going to have a few dominant, quite a few codominant, and then you're going to, depending on the age of the stand, then you're going to kind of deviate from that when we talk about intermediate and suppressed. Okay, so intermediate trees, the crown itself is below the dominant, below the codominant, and it receives some light from above. Okay? Not much, but some, and it's not receiving light from the side. And when I say not receiving light from the side, I mean not receiving direct light from the side. Okay? Indirect light is different, okay? But direct light is not coming in from the side. And then a suppressed tree would be that the crowns of that tree is not receiving light from above. It's not receiving light from the side, and so it receives no direct sunlight. It still can live, and it still can do photosynthesis and create carbohydrates and things like that because of the indirect sunlight that it's receiving, but no direct sunlight. So this is what it would look like kind of in a real forest, maybe an old growth forest in the Pacific Northwest. You might have these Douglas fir trees that are 200, 220 years old, something like that. Dominant canopy. They're dominating the tree canopy. They're taller than everything else. Then you might mix in some ponderosa pines or other pine trees that might be approaching that 200 mark, maybe 150 years old or somewhere in that range. Okay, those are going to be what sometimes is called your sub canopy, but those are your codominant plants. You might have another species of pine or just smaller pines in that region, also part of that sub canopy. Also can be codominant, but it could be also an intermediate class. And then depending on how thick this canopy is, anything in this region, the seedling region, could be considered suppressed. They're not getting light from, directly above, etc. And that, this is, it doesn't matter what year it is. It could be after a fire, you could get a bunch of seedlings. Could be every single year you get a few seedlings. There's, lots of ways at which this can occur. Okay, so again, back to kind of tree age. Now getting at the nitty gritty and actually aging a tree. You age a tree by looking at the annual rings, or what sometimes is called annuli. So trees in the northern temperate region, and the southern region, on the basically moving away from the equator. If you go to the northern regions away from the equator or the southern regions away from the equator, you're going to have seasons. Seasons will drive the formation of annuli or annual rings because you have different periods of growth. You have a fast growth period that's coming out of dormancy, and then kind of a slower growth period, or what's sometimes called the late growth period, which often is indicating by warmer temperatures, maybe summer, drought conditions, etc. So early wood, often called spring wood, and is typically more porous, often it has a little bit more pitch, it has a little bit more sap, lighter in color, and it's an indicator of fast growth. Okay, and then you have late wood or summer wood, sometimes called fall wood. It really depends on where you're at in that region and what your temperatures are like. But this is going to be a darker colored wood, less sap, and less porous. When you're counting rings, you are going to count either the light rings or the dark rings. So you're either going to count how many springs has that tree gone through, or how many summers has that tree gone through. You can do this in two main ways. You can do it with a cross section of tree, which means the tree was cut and you have a cross section showing you all the rings together. Okay, and I'll show you some examples of this and let you practice with this. Or you can do it with what we call a bore or an increment bore sample, which is a core that's taken out of the tree. Okay, and for the most part, doesn't do any permanent damage to the tree. Now, there has been some evidence that if you core a tree enough times, that you can introduce diseases or avenues into the tree to take, and get a disease or get insect pests or something like that can enter the tree. But by and large, it's causing very little damage to the tree, far less than doing a cross section, which is pretty much permanent death, depending on where you're cross sectioning the tree. Nonetheless, both methods are used fairly often. Okay. So this brings me to that more information that you can get than just aging a tree. Okay. So by knowing a tree's age, And knowing the height of the tree. So let's say we take a core from a tree today, and let's say that tree is 58 years old. And let's say the tree is 65 feet tall. We would then be able to say, well, when that tree reached 58 years old, it was 65 feet tall. Well, then someone might say, well, when it was 20 years old, or 38 years ago, how tall was the tree? Okay? We can do that. We can do what's called back calculation, or calculate the age backwards. Okay? You can do this in many different forms. Basically, you can use what we call a von Bertalanffy growth curve, which gives you a growth pattern for the organism that you're interested in. You can do this with anything that you can age to a yearly basis. Okay? I teach fish and wildlife management, and I often teach this same method of analyzing age and growth and size in fish as I do in trees, because they both have hard parts that grow annuli every single year. They're both what we call indeterminate growers. So fish grow forever, their entire life, they're still growing. And trees grow forever, their entire life, they just keep growing. For those organisms, it's easy to back calculate ages. It's also easy to back calculate size. Okay? The other thing that trees can allow us to do, or tree rings can allow us to do, is we can see different marks of the landscape or marks of events in that tree's history inside the rings. Okay? And I'll show you this. It's easier done with a cross section. So if you get a cross section, you can tell when a fire might have came through and burnt that tree. You can see, a lot of times you can see where there might have been insect damage to the tree, potentially disease damage to the tree. These kind of events can show up on those cross sections of the tree. Okay? And then, like I said before, maybe you're really interested in finding out, well, we have this 10-year period recently where it's extreme heat. What if we go back and we say, hey, what about the 10 years before that? What was growth rates? Okay? And then we can make predictions. Well, yeah, in fact, the temperature profile today is definitely causing trees to either grow faster or slower or whatever it might be. Okay? And that's where a researcher would come in to play and ask those kind of questions. And like I said before, management is kind of three fields: ecology or research, sociology, dealing with people, and then economics, dealing with the money side of it. Okay? And so a lot of forest managers, they really like the research part, and the other two pieces not so much. So I'm going to kind of, hit on a lot of those research parts, because I'm guessing if you're a science major, or you're taking this class and you want to go into forestry, it's not because you wanted to do economics. Probably not. Okay, so here you can see the center of the tree is called the pith, or that's called the pith wood. Okay, and then you have a region of the tree which is called the heartwood, and then a region of the tree which is called the sapwood. All throughout the heartwood and sapwood, you're going to have these early wood, late wood bands. Okay, again, the early wood is often light and a much wider band than the late wood. The late wood basically shows you the slow growth of that tree. So you might have this big growth rate for early wood, and then that goes right into a slow growth period for late wood. Okay. We'll get into determining kind of the bark, the depth of the bark and the depth of the cork. These can play a very important role when we're talking about what's the volume of the wood. So if you're running a DBH or a diameter at breast height, you need to account for, well, how deep is that bark? How much of that wood is actually usable? Okay, the bark's not really used when it comes to turning out lumber and things like that. It's stripped off and used for other purposes, but it's important for those kind of pieces. And we'll talk more about that later. Okay, so here you can just see this is a core. You can see the rings, you can see the early ring and then followed by a dark ring. So early wood, late wood, and then you can just see it on and on and on. You can see the bark and the cork, and then you can see the rings. And then here, this picture shows a little bit better. You can see this half moon circle, okay, with a dark spot right there. That's the pith of the wood. Okay, so that's the center of the wood. And so we're interested in just one side. So when you core a tree, I'll show you this, but you want to go into the pith, maybe a few annuli outside of the pith, and then pull it back out. You don't want to go too far. You don't want to go all the way through the tree. Okay, because this side over here is meaningless. You really just want to go into the pith a little bit further and then bring it back out so you can get all the annuli all the way to the edge of the outer bark or the vascular cambium. Okay, but I'll show you this in a later video. All right, so with that being said, like I said before, we are going to examine DBH, or diameter at breast height, the next lecture. And then I'm going to show you videos on how to take some of these calculations and a lot of other calculations too, like, floor vegetation. So what's the density of floor vegetation underneath a forest? That can tell you, how much light is coming through. We'll also look at density of fuel. So we'll estimate how much fuel is stacking up in forests. That can give you an indication of, well, what kind of fire might you have in this region with all that fuel that's stacking up, etc. Okay, so next time we'll look into those issues along with DBH and some other things.